Okay, guys, today we're going to talk about how the reaction rate and the stoichiometry of the chemical equation relate to each other. How is stoichiometry related to reaction rates? So please, before we start, let's make sure you got your Chapter 5 guided notes out and a calculator. You're going to need both. So here we go. Consider this reaction. I think we introduced it last time. But if we look at this chemical reaction, we've got 2 moles of nitrogen dioxide. It's decomposing to form 2 moles of nitrogen monoxide plus 1 mole of oxygen. Now, if you look at the graph over here, we have run this reaction and we graphed concentration on the y-axis and the time on the x-axis. So before we do anything, why is the green line going down? Yeah, it's a reactant, and this reactant is going to disappear over time. Why are the blue and the red lines going up or have a positive slope? Well, because they're products, and over time the products are forming, and so they're going to have a positive slope. But let's look at it a little more closely. If you look here, oxygen gas can appear only half as rapidly as nitrogen dioxide. Gas disappears. So if you look here, the nitrogen dioxide has a really steep slope, but it's negative. Well, how come, guys, the oxygen gas can only appear half as rapidly as the nitrogen dioxide is disappearing? So if you look at the red line, its slope was only half that of the green one. How come? Good. That's correct. You've got to look at the stoichiometry. I'm going to talk about this a lot today. How many moles of nitrogen dioxide are decomposing? 2. How many moles of oxygen are appearing? Only 1. And so that's why this red line, the slope is much more shallow than the slope of this green line. And that's because there's only 1 mole of oxygen forming for every 2 moles of nitrogen dioxide that disappear. Here's another way to look at it. If you look at the other product is nitrogen monoxide. Well, it says here nitrogen monoxide gas appears twice as fast as O2. Again, let's look at the graph. This blue line has twice the slope of the red line. How come? Goes back to the stoichiometry again. For every 2 moles of nitrogen monoxide that form, there's only 1 mole of oxygen that forms. So we're forming twice as much. And so that's going to appear twice as fast as the oxygen. So that's kind of what we're going to talk about today, and we're going to go through and figure out how to determine how much faster one product might form compared to another product, and actually put some numbers to it and quantify it today. Okay, so be following along in your notes. There's something to write down here. It says to relate the reaction rate to the stoichiometry of the reaction, we will use the rate expression. So that's what I'm going to talk about for the rest of the day, is rate expression. It's simply a way to relate reaction rate to the stoichiometry. So the definition for rate expression is right here. The rate expression relates the disappearance of reactants or the appearance of the products to the stoichiometry of the reaction. So it relates the disappearance of reactants or appearance of the products to the stoichiometry of the reaction. The rate expression is also known as the relative rate. So a lot of chemistry textbooks will use these words interchangeably. So rate expression means the same thing as relative rates. So rate expression is the same thing as relative rates. I usually call them rate expressions, but if you hear the term relative rates, it's the same thing. Okay, so let's get into it. Let's learn about rate expressions. So let's consider this same chemical reaction. 2 moles of nitrogen dioxide are decomposing to form 1 mole of oxygen and 2 moles of nitrogen monoxide. Well, when we write the rate expression for a reaction, very important, okay? When we write them today, we've got to remember that the rate of change for reactant is always negative. Why is the rate of change for a reactant always negative?
It's going down.
Yeah, good. Its concentration is decreasing over time. It's disappearing. So it's got a negative slope. Good. And the rate of change for the product is always going to be positive. Again, why? Well, the products are forming over time, so their concentration is going up over time, so the slope is going to be positive. All right, and this might be the most important thing of the day, so I'm going to put a star by this one. The simplest way to obtain a rate expression is to place a 1 over each coefficient in the balanced chemical equation. So we're going to put a 1 over the top of the coefficient in the balanced chemical equation. I'll show you what I mean by that in just a second. So, if we were going to write a rate expression for this chemical equation, I'm going to show you how you would do that. Okay, and this is what you're going to be doing the rest of the day, so please watch. We're starting with a reactant. It's on the left side. So what's going to happen to this reactant? Is it going to appear or disappear? Disappear. So my sign needs to be what? Reactant, the sign is negative. So I'm going to start with a negative sign. Now I've got a coefficient of 2. What do I put over the top of that 2? A 1. So I'm going to put a 1/2. I put a 1 over the coefficient. And then we're simply going to times it by its rate, which is the change in the concentration of NO2 over the change in time. Remember when we talked about a rate in chemistry? It's the change in concentration in terms of molarity over change in time. Well, another way to tell people that you're taking the concentration is to use brackets. And so sometimes you'll see, most of the time you'll see brackets right there. It's simply saying the molarity. So the change in molarity over the change in time. All right, now we set that equal to the other terms in our equation. So let's go to the other terms. Well, we've got oxygen here. It's a product. So is it going to be appearing or disappearing over time? Appearing. So products, the sign is always what? Positive. So we're going to keep it a positive sign. Now the coefficient is a 1. Could I put 1 over 1?
You could, but just the 1.
Yeah, you could put 1 over 1, but it's just 1. So I'm going to leave that off. And now it's just the change in concentration of O2 over the change in time. So this whole term, what we're writing here, this is the rate. This is the rate at which oxygen is going to appear. It's equal to, now let's go to our last term. We've got nitrogen monoxide. It's a product, so is the sign going to be positive or negative for it?
I have a question.
Wait, it's equal to?
Is it equal to, or do you add
Yeah, no, we set these terms equal to each other.
all of them?
All of them. Yep. We're going to set all of the terms equal to each other. And I'll show you why here in a second. So let's go back. Is it a product or a reactant here? Product. So the sign is going to be positive. Products, the sign is always positive. So we're going to keep it positive. Now my coefficient is a 2. What do I put over the top of it? 1 over 2. Now we're going to times it by its rate. the change in concentration of nitrogen monoxide over the change in time. Okay, what we just wrote right there, guys, this is called the rate expression. Some people call it the relative rates.
Is it supposed to be an equal sign between O2 and NO? Or is it
Yes, all of these terms, guys, are set equal to each other. So we have this term, and this term in this equation. We set them equal to each other. And so that's why some people call them relative rates. Where we're going with this, guys, if we knew the rate at which NO2 was disappearing, could I then use that to solve for the rate at which oxygen is appearing?
Yeah.
We could. And that's where we're going. We're actually going to quantify this in just a second. But we've got to get used to writing what is known as the rate expression.
So that's the answer.
That's your answer. Okay? And so let's see if we got that right. A negative 1/2 times the rate of NO2 is equal to, this one's positive, we kept it positive, the change in concentration of oxygen over the change in time is equal to positive 1/2 times the change in concentration of NO over the change in time. And so we did get it right. It's known as the rate expression. I've got a lot of practice problems coming up. Please stay with me. I promise if you pay attention, we'll get this by the time we're done. Practice problem number 3 says, to write the rate expression for the following reaction. Let me help you get started, and then I'll give you some time to do it. This is a reactant, so the sign is going to be what? Negative. We have a 4 as a coefficient. What do we always put over the coefficient? A 1. Okay, there's my hint to get started. So please try it. Write the rate expression for this chemical reaction. If you're watching the video, please hit pause and try it until you get an answer. Okay, so hopefully at this point you have an answer. But I would like to go through and show you how I would approach a problem like this. Okay, so we're starting over here with this term. It's a reactant. It's going to disappear over time, so it's going to be negative. We put a 1 over the coefficient, so it's a negative 1/4. And then we simply times it by the rate. The rate is the change in concentration of pH3. Always put brackets around the formula. That tells you this is change in concentration, divided by the change in time. That's it for that term. We set it equal to all the other terms. Now we're going to this side of the equation, which is the product side. Positive or negative sign? Positive, because it's going to appear over time. And so my coefficient is a 1. Yeah, I could put 1 over 1, but everyone knows that's just 1. So 1 in chemistry is implied. So all we're going to do is times it by the rate. The change in concentration of P4 over the change in time. That's it. So set it equal to your last term. Again, it's a product. Positive or negative? Positive. It's going to form over time. So I'm going to keep the sign positive, but my coefficient is a 6. What do I need to put over the top of it? A 1. So it becomes 1/6 times the rate, which is the change in concentration of H2. Again, use brackets, over the change in time. And that's it. How many of you guys got that right? Okay, very good. So this is my answer. That is the rate expression for this chemical reaction. Okay, very good. Before I move on, what is this telling us, guys? What is this part telling us? This is the what? The rate at which pH3 is disappearing over time. It's negative because it's disappearing. So those are a couple of the points that I hope that you're recognizing right now. Okay, so let's see if we got it right. A minus 1/4 times the rate, pH3 over time, is equal to positive, and we kept it positive. The change in concentration of P4 over the change in time is equal to positive 1/6 times the change in concentration of H2 over the change in time. Okay, so very good. Practice problem number 4. I hope that we're getting this, but it says to write the rate expression for the decomposition of nitrosyl chloride, which is NOCl. Here's the balanced chemical equation. So let's write the rate expression for that. If you're watching the video, please hit pause at this point and write the rate expression. Once you have your rate expression written, then hit play and see if you got it right. Okay, hopefully at this point you have tried it and you've got a rate expression. Let's see if you got it right though. Okay, this is a reactant. It's going to be negative because it's disappearing over time. We have a coefficient of 2. We need to put a 1 over the top of that. So it's a minus 1/2 times the rate, which is the change in concentration of NOCl over the change in time. We're going to set that equal to the other terms. Let's move on to this nitrogen monoxide. It is a product, so it's going to be forming over time. It's going to be appearing, so its sign is going to be positive. My coefficient is a 2, so I need to put a 1 over the top of it. Becomes 1/2 times the change in concentration of NO over the change in time. Okay, let's move on to the last term. Again, it's a product. It's going to be positive. My coefficient is a 1, so I could put 1 over 1, but it's just equal to 1, and 1s in chemistry are implied. So let's just times it by the rate. The change in chlorine, the change in the concentration of chlorine, over the change in time. Okay, that is the answer. Guys, look up here. How many of you guys got that? Okay, very good. Very good. So let's make sure we got it right. And yes, we did. Okay, now what I would like to get into is how a chemist would actually use this information. How would they use the rate expression in chemistry? We're going to quantify it and figure out different rates now. So let's go to practice problem number 5. It says to consider the following reaction in which ozone, guys, is O3, is converted into oxygen, which is O2. This one has a couple parts. On part A, it says to write the rate expression for this reaction. So I'm going to hit pause right now. If you're watching the video, go ahead and write the rate expression for this chemical reaction. Once you have the answer, then go ahead and hit play and see if you got it right. Okay, so hopefully you have an answer at this point. So I'm going to write the rate expression for this reaction. I'm going to do it up here though. So let's start with this first. It's on the left side, so it's a reactant, which means its sign is going to be what? Negative. So I'm going to put a negative sign in. Now my coefficient is a 2, so I need to put a 1 over the top of it. So it becomes 1/2. Times the rate, which is the change in concentration of ozone, over the change in time. Let's set that equal to our other term, which is a product. So the sign is going to be positive because it's appearing over time. My coefficient is a 3. So I'm going to put 1/3. Now we're going to times that by the rate, which is the change in the concentration of oxygen, O2, over the change in time. And so there's my rate expression. How many of you guys were able to get that correct? Okay, very good. Now let's go to part B, where we're going to quantify this and actually use the rate expression to do something. So it says on part B, if the rate at which oxygen appears, so oxygen is appearing at this rate, 6.0 times 10 to the minus 5. Now pay attention to the units, molarity per second. So our time is measuring in seconds, our concentration is in molarity. So if that is the rate at which oxygen appears, at what particular instant, what rate is ozone disappearing? at the same time. So here's how a chemist would use the rate expression to figure this out. Okay, I'm going to rewrite the rate expression down here. I want you guys to write everything that I'm writing right now. So minus 1/2 times the change in concentration of ozone over the change in time is equal to, I'm just rewriting this rate expression, 1/3 times the change in concentration of oxygen over the change in time. Now, a couple of things that I hope you guys will recognize. It gave us the rate at which oxygen is appearing. Where do you see the rate of oxygen in our rate expression? This term right here is the rate. It's the change in concentration over change in time. That's what the rate is. So this whole term right here is what it's referring to. So we can substitute this 6.0 times 10 to the minus 5. We're going to take that number right here, and we're going to substitute that in and plug it in for the rate. Okay, and so when we do that, here's what we get. We still have a minus 1/2 times the change in concentration of ozone over change in time. It's equal to 1/3. Now, this is the rate at which oxygen will appear. It told us was 6, so all I'm going to do is times it by 6.0 times 10 to the minus 5. That's it. So what we've just set up is a math equation with one unknown, and that's the rate at which ozone will disappear. So if you want to think about it in terms of something you're familiar with, all you're going to do is call this term that I just put a box around, you're going to call this term x. And we're going to solve for x. So what I would do first is take the 1/3 and times it by 6.0 times 10 to the minus 5. So 1/3 times 6.0 e to the minus 5. And I'm going to rewrite it over here. So I've got a minus 1/2 times the change in concentration of ozone times the change in time is equal to, now what I did was times these two numbers together, and I got this number, 0.00002. If you want to write it in scientific notation, that would be okay too. Now, what I'm trying to find is the rate at which ozone is disappearing. This is the term I'm trying to find. So if that's my x, I want to isolate it. I want to get it by itself. How do I get rid of this minus 1/2?
Divide by times by 2.
Times by 2. Could I times by a minus 2 on both sides?
Yeah,
I would actually times by a minus 2. Why a minus 2?
because it's minus.
Yeah, because that would get rid of your minus sign. And by timesing by 2, you get rid of the 2's. And so all we're doing there is isolating the rate at which ozone is disappearing. So let's take that and times it by 2. You should get this number. Negative, wait, would it be negative? Yeah, negative 0.00004. What are my units going to be, guys? It's a rate, so it's molarity per second. Okay. That's the answer, but let's talk about it for a second. Guys, why is the rate negative? Yeah, because it's the rate of ozone. Ozone is going to disappear, so it's going to be a negative sign. So that's something to watch out for. Here's another question. If we switch this rate of oxygen to standard form instead of scientific notation, guys, which rate is larger? The 0.00004 or the 0.00006?
6.
Yeah, this is larger. Why is the rate at which oxygen appears larger than the rate at which ozone is disappearing? This is the whole crux of this lesson. Good. If we look at the stoichiometry, there's 3 moles of oxygen that are appearing for every 2 moles of ozone. So this one, oxygen, is going to appear at a faster rate than that at which ozone disappears. So that's all we're doing, is figuring out the relative rates of these guys. Does that make sense? Let's go to another practice problem. I got one more practice problem, and let's see if we can make sense of this. Practice problem number 6. Oh, let's see if we got the answer right. So B was in -4 times 10 to the -5. And yeah, if we wrote this in scientific notation, that's what it would be. Okay, practice problem number 6. This is the last one of the lesson, so please watch. Let's try and get this down. So there's a few parts here. Let's start with just part A. It says the decomposition of dinitrogen pentoxide produces nitrogen dioxide and oxygen gas. Part A says to write a balanced chemical equation for this reaction. This is going back, and we're going to use all of the skills that we've learned in chemistry to figure this out. Okay? So before I let you try it on your own, guys, what does the prefix di mean? 2. So how many nitrogens do we have here? 2 nitrogens. How many oxygens? Pent is 5. So that's N2O5. Well, it looks like it's decomposing, so I would draw the arrow. Nitrogen dioxide and oxygen gas. So please come up with the chemical equation and then balance it. Let me give you some time. If you're watching the video, please write the equation and then go ahead and balance it on your own. Once you have an answer, hit play and see if you got it right. Okay, so hopefully at this point you have wrote the chemical equation and then balanced it. So I'd like to go through that with you. Dinitrogen pentoxide. If we have a subscript or a prefix here that's di, that means how many, guys? 2. So I'm going to put N2 pentoxide. What does pent mean? That's a prefix that means what? 5. So we got O5. That's dinitrogen pentoxide. Well, it's decomposing, so I'm going to draw my arrow, and it produces nitrogen dioxide. What does di mean? 2. Now this one doesn't have a prefix for the nitrogen, so what does that mean? It's just 1. So this is N1. Do I need to write a 1? No, it's implied in chemistry. Dioxide is O2. What do I write for N? A plus sign. Good. So we plus oxygen gas. What is the symbol for oxygen? O. Now, is it a diatomic element? It is. So what do I always put with diatomics? A little 2 right there. That's the chemical equation, but is it balanced? It's not. So let's go, and let me go quickly here on how to balance it. So the difficult thing about this problem is going to be your oxygens. Guys, can I ever get 5 oxygens on the right side? No. So it looks like I can only get an even number on the right. So what's the next even number I could get to? 10. I'm going to put a 2 right here. That gets me to 10 oxygens. But how many nitrogens do I have? 4. How do I get to 4 nitrogens? I need to put a coefficient of 4 right there. If I do that, how many oxygens do I have now? There's 4 times 2, that's 8, plus 2 more is 10. Is that balanced? It is. Okay. And so there's the balanced chemical equation. So this is part A. How many of you guys got that before I did it? Okay, very good. All right, let's go to part B. And you guys should be able to do this because it's just writing the rate expression. So please take a second, write the rate expression for the balanced chemical equation. If you're watching the video, please hit pause. Write the rate expression, then once you have your answer, hit play and see if you got it right. Okay, so hopefully at this point you have B completed and you've wrote the rate expression. Here's how I would write the rate expression for this balanced chemical equation. Start with the reactant, so it's going to be negative. We put a 1 over the coefficient, so it's a negative 1/2 times the rate at which dinitrogen pentoxide is changing over time. Okay, let's set that equal to the other terms here. Our product, so it's positive, and I'm going to put a 1 over the coefficient was 4, times the change in concentration of nitrogen dioxide over the change in time. There's one more term. It's a product, so it's positive. The coefficient is just a 1, so I could put 1 over 1, but I don't need to. Change in concentration of O2 over the change in time. Okay, there's my rate expression. So this is the answer for B. How many of you guys got that? Very good. Now let's go to part C and try to understand how a chemist would actually use this information. How do they use rate expressions? Part C. If the rate of decomposition for the reactant at a particular instant in a reaction vessel is 4.2 times 10 to the minus 7th molar per second, what is the rate of appearance of the two products? Now, before I let you try this one on your own, there's an important point, guys. We're talking about the decomposition of this reactant. It told us its rate. But guys, the rate of the reactant is going to disappear. So what do we need to put as the sign for this rate? It's going to be negative. So if you guys would put in a negative sign for that 4.2 times 10 to the minus 7th, you've got to do that because, again, this was a reactant. It's going to disappear over time, so its rate is going to be negative. Okay, so at this point, I think we've done a problem like this. You're going to use the rate expression. Where are you going to plug in this negative 4.2 times 10 to the minus 7? Where do you plug it in at? Yeah, that's the rate for this guy. So you're going to plug that number in right here. And then all you got to do is solve for the rate at which NO2 is going to form, and also solve for the rate at which oxygen is going to form. Let me let you think about that for a second. Please try it. Give it some thought. Okay? See if you can solve for the rate at which nitrogen dioxide is forming, and also the rate at which oxygen is going to form. So if you're watching the video, please hit pause at this time until you get an answer. Then hit play and see if you got it right. Okay, so hopefully at this point you've answered C and you found the rate of appearance of the two products. I would like to show you how I would approach this problem. So I don't have much space, so I'm going to write real small down here. But what I'm going to do is use this rate expression. Again, this was the rate at which the dinitrogen pentoxide is disappearing. So I'm going to use that. So we've got the rate expression. It said a negative 1/2. And I'm going to, this is the rate at which it gave me right here, was a minus 4.2 times 10 to the minus 7th. Now let's set that equal to the next term, which is the rate at which nitrogen dioxide is going to appear. But I've got to include this 1/4. Now I'm going to put in the change in concentration of NO2 over the change in time. So this term right here is the rate at which NO2 is forming. That's what I'm solving for. If you want to just call this whole thing X, That's what we're doing. So what I would do first is take a negative 1/2 times by a negative 4.2 times 10 to the minus 7. So let's do that. And switch it to scientific notation. Guys, you'll make a lot less errors if you do that. So I'm getting this number. So 2.1 times 10 to the minus 7th is equal to 1/4 times the change in concentration of NO2 over the change in time. Okay. Now, if this is the term I'm solving for, this is my x. How would I get rid of this? How would I get rid of this 1/4? Well, I got to times it by 4, both sides. If I times it by 4 over here, the 4's will cancel out, but I got to times it by both sides. 4's cancel there. And so let's take that 2.1 times 10 to the minus 7th and times it by 4. So what I get is that the change in concentration of NO2 over the change in time is equal to a positive 8.4 times 10 to the minus 7. What are my units going to be, guys? Molarity per second. Okay, so guys, hopefully you have that answer. What we just solved for, the rate at which nitrogen dioxide is going to form is 8.4 times 10 to the minus 7th molar per second. All right, that's only one of the products. Now we've got to find the rate at which the other product is going to form. How do we do it? The exact same way. And so here's how I would set that up. Again, we're going to use this rate expression. So we start with the minus 1/2. Timesing it by the rate at which the dinitrogen pentoxide is disappearing, which is a negative 4.2 times 10 to the minus 7. We're going to set that equal to this term in our rate expression. Notice it didn't have a coefficient, so it's just the rate, which is the change in concentration of O2 times the change in time. So this one's very easy. We just take a negative 1/2 in our calculator, a negative 1/2, and times that by a negative 4.2 times 10 to the minus 7. So my rate at which oxygen is going to form is equal to 2.1 times 10 to the minus 7. And again, my units, molar per second. All right, there's the answers. But guys, more importantly than the answers, I hope that you can understand the next few questions that I ask. Let's try and understand what this means. Yeah, we got a bunch of numbers here, but what do they mean? What are they telling us? So I want to ask a couple of questions. If we look at the rate at which nitrogen dioxide formed, it was 8.4 times 10 to the minus 7. How does that relate to the rate at which our dinitrogen pentoxide was disappearing? Well, that was negative 4.2 times 10 to the minus 7. How do these relate, guys? Look at this. Look at these numbers right here, 4.2 and 8.4. How do they relate? Yeah, it's exactly half. Why, guys, is the nitrogen dioxide forming at twice the rate that the dinitrogen pentoxide is disappearing? Why is that? It goes back to the what? Stoichiometry. Guys, look. When 2 moles of dinitrogen pentoxide decompose, it forms 4 moles. That's twice as many moles. So, of course, the rate at which the nitrogen dioxide formed is going to be twice as much. Do you see that relationship there? 4.2 times 2 is 8.4. Now, Let's look at the other product, which was oxygen here. How does its rate of appearance relate to the disappearance of the reactant? It's what? It's 1/2. If you take 4.2 and divide it by 2, you get 2.1. Again, let's look at the balanced chemical equation. We had 2 moles of the dinitrogen pentoxide, and it forms 1 mole of oxygen. So that is why the oxygen is only forming at half the rate. It's relating it to the stoichiometry of the balanced chemical equation. Incredibly useful stuff for chemists. They can figure this out before they even run the reaction, and they would know what to expect. It's something that they would use all of the time. Okay, I know that this stuff's a bit complicated. Okay, so I've given you some extra practice in your student workbook. So let's go to the worksheet in the student workbook titled Rate Expression Worksheet and get that done. Again, it's called the Rate Expression Worksheet, and hopefully this video helped.